In the previous class, we have gone through the Jfet, introduction to FETs and the different types of FET, and how the Jfet is being constructed. So we have seen the construction of Jfet, like it will be an N-type substrate on which we will be diffusing two different gates of opposite type, like it is of N-type substrate is there, then P-type of gate will be there. So whatever the substrate will be there, that will define the type of Jfet. Here the substrate is of N-type, so it will be like N-channel Jfet. So the space between the gate and the two different gates, the space between the two different gates is considered the channel. So channel is of N-type, so it is of N-type Jfet. Okay. So we've also seen the Jfet basically works in reverse bias case. Okay. So this is the working setup in case of Jfet. And if this is a N-channel Jfet, then we can just write it as working setup for N-channel Jfet. Okay. So here we will be providing a negative gate voltage to the gate. Okay. So this gate need to be reverse bias if this Jfet is going to be operating. Okay. Here this a negative application of gate voltage will be controlling the current flowing through this channel. If this channel is this much, the current will be high. If we are going to increase the negative gate voltage, then it will be reverse bias. More reverse bias will be there, so depletion region will increase. Okay, so there will be an increase in depletion region this side and this side. So that means there will be less channel available for conduction. So if less channel is available, the current flow or the number of charge carriers that will be flowing will be reduced. So that will be defining the control flow, so the current flow. So this VGG or VGS we can say. So this is VGS. So VGS is going to control the current. Okay. So here voltage is controlling the current. Opposite to like in BJTs. In BJTs, the current were controlling the current. Here voltage is controlling the current. So the main motive is we need to control the current through the applied gate voltage. So here we will start. So the working of Jfet is like it works with reverse biased gate to source junction, we can call it. Okay. So source to junction, gate to source region is reverse bias basically. Okay. And we will be varying this drain to source voltage. So as we are increasing the drain to source voltage, the current through this at constant gate voltage, gate to source voltage, as we are going to increase the drain to source voltage, there will be an increase in current. Okay, so the current will be increasing with the increase in drain to source voltage. Okay, so here if we are going to one more point, if we are going to apply the VDS to the channel, basically the channel region is going to reduce. So as we are going to apply as more negative gate to source voltage, channel width decreases. This will decrease the number of charge carriers reaching to drain side or drain terminal. So it will basically reduce the ID, that is drain current. Okay, so this is the main motive. So we will start with like how the effect of gate voltage is there on the channel width. So here, from here we can see if Jfet biased for conduction, so this will be a reverse bias voltage. Gate to source voltage is a reverse bias, and drain to source voltage with respect to that will be biased at a constant VDS. Okay, so this VDS and gate to source voltage VGS is going to define what is the channel width. So we can consider here, so initially it is whatever gate to source voltage we have applied, channel width is this, so this is the channel width. Okay, so in the next case, if we say if we are going to apply greater VGG, that means we are going to apply with greater VGG, that means greater VGS. So if we are going to increase the uh, VGS in negative direction or in opposite, you can say in negative, because we have biased in opposite, like it is reverse bias. So if in reverse bias we are going to make it more negative, then it will narrow the channel. So the channel between uh, these two gates will be narrowed. Okay, in the comparison to the previous one, we can just see here it is being narrowed. Okay, so the between the wide areas we can just see, so what is the space available in the wide area, which increases the resistance of the channel and decreases the ID. So okay, so here the resistance of this channel is being reduced, increased, and the current will be reduced. It is like this complete channel, you can just consider the case. So here of this channel, so this is your drain and this is your gate. Okay, so if we are applying the negative gate and here we are applying the positive VDS. Okay, okay, so here once if we are applying like VGG, that is negative, if we apply it a zero value, suppose this value is 0, VGG is 0, that means the VGS is 0. At that time, this channel region is represented by an equivalent resistance. Okay, that means at this point, the resistance will be less. If we consider this resistance up to here, the resistance will be suppose 1 ohm. Then by combining here, it will be like 1 ohm. So overall, it will be 2 ohm. So similarly, it is just a representation. That means resistance, if we consider the whole complete the channel region, this will be having a resistance. So if we consider the case like some current is flowing with respect to this, then there will be a voltage drop also. So the voltage drop at this point will be high because here the resistance is high. Okay, so the current direction is this way. So that means here the positive and negative like voltage drop will be there. So the voltage drop here, suppose 2 volt is there, here 1.5 volt will be there, here 1 volt will be there, voltage drop if we talk about the voltage drop. Okay, and similarly at downside, here it is 1 volt, suppose here 0.5 volt is there, so this will be the voltage drop. Okay, so if uh, whatever gate voltage we have applied, with respect to this channel is considered to be a resistive circuit, like it will be having like an resistance. Okay, so if we are going to increase this uh, gate to source voltage, the resistance uh, between these drain and source will be like going to increase here. That same it is going, the channel, as the channel is going to increase, channel depletion is going to increase, our channel width is going to reduce. At that time the resistance will be increasing. Okay, so as the resistance will be increasing, the current will be decreasing. Okay, in this region. So similar is the effect. And one more concept is like the current or the value of this depletion region is plotted like this. Okay, that means the depletion region on upper side or on drain side, this is drain side and this is source and this is here. So the depletion region on drain side is considered to be high than the source side. Why? Because whatever gate voltage, suppose this gate voltage we have taken is 0. Okay, this gate to source voltage is 0, that means it is connected to 0, and this is 2 volt. So this is 2 volt and this is 0. So this side is more reverse bias because it is 2 volt. On this side, okay, here 1.5 volt is here. So this side and this one is less reverse bias because it is 1.5 volt is there. On this side it is 1 volt only. So here it is even less reverse bias. So if it is less reverse bias, it will be having smaller depletion region. If it is more reverse bias, it will be having larger depletion region. That's why the depletion region is more towards the drain side. Okay, this is depletion region is more towards drain side. Okay, so we were talking about the gate to source voltage. So as we are increasing the gate to source voltage, the depletion width is going to reduce. So here this is the depletion width. Okay, in further case is like if we are going to apply the gate to source voltage less than this one case also. So it is the case of greater than, this is the case of greater, and this is the case of lesser VGS. So if we are increasing the VGS in negative direction greater than this, then the depletion width will be high, or the channel width will be reduced. In this case, if we are reducing the gate to source voltage less than this one, whatever applied we here, so if we are going to reduce the gate to source voltage, then it will be less, you can say reverse bias, then the depletion region will be reduced and the width will be high. So channel width is greater. So if this is the case of 1, this is the case of 2, and this is the case of 3, then the channel width in case of uh, 3, in case of 2 will be lowest than the channel uh, of 1, and then the channel width of 3. So channel width of 3 will be highest as it is biased with less negative or less reverse bias amongst all. Okay, so this is how the gate to source voltage is going to affect the channel width basically. Okay, so next we will see, like if we are going to operate the same, so we are going to operate the Jfet operating at VGS is equals to 0. So if VGS is equals to 0, at that time how this Jfet will be behaving, we will see that. So if we are considering the VGS is equals to 0, that means whatever gate to source voltage we have applied, that is a 0 across the gate to source terminal. So this will be the setup. Okay, so this is the setup where VGS is made 0 and VDS, basically VDS is going to vary. VDS means we are going to vary the VDD. So if we are varying the VDD, with respect to that VDS will be varying. Okay, so how the current variation will be there? That means we are going to plot the drain characteristics. So drain characteristics is nothing but the output characteristics. Okay, so this will be the drain characteristics when VGS equals to 0. Okay, so if VGS is 0, at that time, if we are going to increase the VDS, okay, so here we are increasing the VDS. So if VDS is 0 and VGS is also 0, then the current will be 0. That will be the location of A point. This is the A point. Okay, so we can just write the first case, VGS is 0 and VDS is 0. This will be resulting the current ID that will be 0 at A point in the graph. In the graph it is written. Okay, so the next we will see here, as we are going to increase the VDS, the current is continuously increasing in linear manner. Okay, so this is going to behave like a linear device. So linear device, it is behaving like an resistance. Okay, so if resistance is there, it follows Ohm's law. Okay, so what is that? It will be behaving like this. So if we plot the current with respect to voltage, there will be a constant slope. So this slope will be giving you out I by V, that is 1 by R. So this is giving out the resistance. So this slope gives the 1 by resistance. So this is the relation in case of linear device. So in this case also here, as we are increasing the VDS, the ID is going to increase the linearly. Okay, that means in this region it is going to behave like a resistor. So the channel region in this case will be behaving like a resistance. That's why it is called ohmic region. Okay, so it is called ohmic region. So in the previous discussion we have seen this as the characteristics. So here VGS is 0. Okay, and at that time we are increasing or we are varying this VDD. So as we are varying the VDD, VDS will be varying. In that case, this channel region will be behaving like an resistor. Okay, so it will show the whatever voltage drops will be there, that will be across the resistor, that drops are available. Okay, so in this case, when Vg is equals to 0, Vgs is equals to 0 and Vds increases. Okay, increases up to, we are increasing up to Vp voltage. So we are going to increase up to Vp voltage. Okay, so we are increasing the VDS up to Vp. Okay, in that region, the Jfet will behave like a resistive device, and also it follows the Ohm's law. Okay, it will be following the Ohm's law. In that case, here uh, it will be following Ohm's law, and the curve ID versus VDS will be linear curve. Okay, so we can see from here, and beyond this region beyond this region, this will be showing a constant current. Okay, so the point B, this point is called pinch off point. Okay, or the pinch off voltage. So when VGS is equals to 0, when VGS is equals to 0, and when VDS is equals to VP, at that time what happens inside the device? So this is the case where VGS is equals to 0 and VDS is equals to VP. VDS is equals to VP. This is the pinch off point. This is the point when uh, we have seen in the previous slide. As we are going to increase the gate voltage, the depletion region is going to uh, increase, like this depletion region is increasing. Okay, so pinch off is the point when the depletion region is such that it has reached the case like both depletion region touches each other. That means there will be no channel in between these two gates. So even in case like if gate to source voltage is 0, then also the depletion region is going to increase based on the increasing VDS. If we are increasing the VDS, then also the gate to source voltage uh, is 0, then also VDD will be going to increase the depletion region. So there will be a time when these two depletion regions will touch each other. That means there will be no gap between the depletion region. That means there will be no space available. That means there is no channel. So if there is no channel, whatever current were flowing previously, the same current will be flowing. That means the current will become constant at that time. Okay, so at that time, this is the pinch off point. So beyond pinch off point, if we are increasing the VDS, current will not be increasing in linear manner. After that, the current will become constant, and that constant current is called IDSS. Okay, so this is called the IDSS. So this is ID is the called the saturation current. Okay, so IDSS here will be defined by the term like it has saturated the current. So the current flowing in the Jfet after the pinch off will be called the saturation current. Okay, so this is called the saturation current. So this is the minimum current that will be flowing even if the channel has been completely reduced. Okay, so this will be the minimum current that will be flowing while the pinch off has occurred. Okay, and this is the reason. So beyond this, the operation is called the active region. Okay, or the constant current region, or also we call it the saturation region. Okay, so here when pinch off occur, this is the time when channel region or channel width, we can call it, so the channel width reduced to 0. Okay, or also we can call like put the point like the uh, depletion, both gate side depletion regions touches each other. This is the point called pinch off point. Okay, so at pinch off point, the current will be the minimum current that will be flowing, that is IDSS, and beyond that also the same minimum current will be flowing, that is IDSS. That means the current will become constant, and this is the point C. So further, if we are increasing the VDS, Okay, if we are increasing the VDS further, there will be a point where the current passing through this Jfet will suddenly increase. So this sudden increase in the current will be due to the breakdown of the device or breakdown of the Jfet. So this is basically the breakdown voltage. Okay, so this will voltage is the voltage where the breakdown has occurred. So this region is generally avoided because beyond this the Jfet will damage basically. Okay, so we need to avoid this breakdown region. So generally if we are going to operate the FET as an amplifier, this FET can be worked as an amplifier, so we need to operate it into this active region. Okay, so generally the saturation region is also called the current saturation region or the pinch off region. Okay, based in pinch off region, basically as we are going to increase the VDS, as VDS is going to increase, then the drain current will be a constant current. So drain current has become a constant current, and that constant current will be IDSS. So how these currents and voltages are related, we will see like how the relation of Jfet current and voltage are there. We will see next once we have explained the operation. Okay. So here are some, yes, this is the uh, figure showing the pinch off point. Okay, so this is the pinch off. So pinch off occurs when VGS is equals to 0 and VDS is equals to VP. So when VDS is equals to VP, at that time the depletion region has touches. Both the depletion region touches each other. Okay, so there is no channel available. So this is called the pinch off point. So this is the Jfet action that produces the characteristic curve for VGS equals to 0. So VGS equals to 0 we have seen in the previous case. This is the VGS equals to 0 curve. This is the VGS equals to 0. At that time, whatever the VDS is increasing with respect that there is a curve. So how it has produces, just we can consider here. When VDS equals to 0, at that time the current will be 0. The first case we have seen. As here ID increases proportionally with VDS in the ohmic region. So in the ohmic region, the linearly proportional proportionality of the current with respect to VDS will be taking place. And next is when VDS equals to pinch off, ID is constant and equal to IDSS. This is called the pinch off, and beyond pinch off, this is pinch off basically. And the next is as VDS increases further, ID remains constant at IDSS until the breakdown occurs. Okay, so this is just the explanation of the curve that is available. Okay, so the next we will see the case when there is some gate voltage is applied in reverse bias case, and then we are going to increase the VDS. So the second case, so in the first case it was like when VGS equals to 0. Now we will see VGS is less than, case 2 is like VGS is less than 0 and VDS okay. So VDS is increasing, at that time VGS is less than 0. Okay. So in the first case we can write this is the case 1 and this is the case 2. Okay. So here we are going to operate the Jfet with VGS less than 0. So this is the case where we are going to reduce the VDS. Initially it will be when VGS equals to 0, at that time whatever the current is flowing after pinch off, that current will be IDSS. Okay, so in that case this is IDSS. This will not be IDSS, even if here the current here pinch off is also taking place, but the IDSS, this will not be IDSS. IDSS will be when the pinch off occurs at that time when VGS equals to 0. When VGS equals to 0, at that time the current that will be flowing at pinch off will be IDSS. So as we are going to increase the VGS in negative direction, like it is -1, -2, -3, -4, and so on, we will be getting the reduction in the drain current. This reduction in drain current is because of the reduction in the channel width. Okay, so in the previous concept we have seen, as we are increasing the reverse bias voltage, then the channel width was going to increase. Sorry, channel width is going to reduce and depletion region was going to increase. Okay, so with respect to that, as the channel width will be reducing, the current will be reducing. Okay, so similar graph will be there, but channel this plot will be like it is having the reduced current with respect to the VGS equals to 0. So also this is the pinch off when the VGS equals to 0. Similarly, in VGS equals to -1, the pinch off has shifted to a lower value. Okay, so pinch off will also be occurring, but this pinch off will be at lower value. Okay, so here lower value is there in case of pinch off. And further, if we are increasing the VGS, there will be a time where we will be applying the VGS such that VGS will be causing almost a zero current. Okay, so almost a zero current will be there when VGS equals to VGS off. We will be talking. So we will be talking like that Jfet is being off. Whatever reverse bias voltage, get to source voltage we are going to apply at that time, the VGS will be causing the complete uh, pinch off like structure. So that will be called as the off current or the off side. Okay, so we will just analyze like what is the uh, relation between the pinch off voltage and the cutoff voltage. Okay, so we can just correlate this. This is the curve when we are having different VGS in negative side. So we will just correlate the 2 points, like how this is going to change in case of the pinch off and in case of like cutoff. So we have 2 different points. Okay, so okay, so let us explain this. So one point is pinch off. So pinch off occurs when VGS is equals to 0 and VDS is equals to VP. Okay, at this point also channel width is almost equals to 0, and the current here, the current ID is equals to IDSS. Okay, and another point is cutoff. Channel cutoff is there, or the cutoff voltage. So the cutoff voltage is the voltage when VGS is not equals to 0. VGS is equals to some value that is called VGS off. Okay, VGS off, and at that time, the VDS can be like any value. Okay, at that time, like this is the gate to source voltage. The VDS can be any value, but the current will become 0. So it is like this VDS and like VDS is varying. Okay, so VDS is any value, but when VGS will be equals to VGS of, at that time also the channel width will be like reduced, and the current will here, the channel will be reduced almost zero, but the current that will be flowing is similar to a zero current. Okay, so the current will become a zero in this case, like cutoff region case. But these 2 points are generally used interchangeably. That means this this is the VGS value, and VGS value is in negative direction. That means whatever VGS value will be there, that will be a negative value, or negative value, or the voltage negative value, or the voltage uh, in opposite direction. So voltage is in opposite direction, we are applying the negative direction. But here VDS, in the case of pinch off, so VDS is, this is a positive value, it is a positive value. Okay, so this VDS, that is having the VP pinch off point and the cutoff point. So these 2 points, two voltages are almost constant in all cases, like almost equal. So VP mod of, we can consider mod of VP is equivalent to mod of VGS of. It is same, its magnitude is almost same. Okay, in all cases we will be considering that it is a constant, but the only difference is, if VP is positive, then VGS will be negative of the same magnitude. But if VP is negative, the VGS will be positive. Okay, so if VGS is negative, that means it is for N channel. So for N channel, the VP will be positive and VGS will be negative. In case of P channel, the VGS will be positive, okay, and VP will be negative. So these two are of same magnitude but is of equal opposite nature, and both have the similar functionality. Like in this case, the current, the channel width has reduced as the depletion region increases because of the VDS application. We are going to apply the VDS higher, the channel width is going to reduce, and ID is equal to IDSS. But in case of VGS off, we are going to apply the reverse bias gate to source voltage. In that case, the channel has reduced and the ID becomes zero at that time. So this is your ID is zero. That means this current, so this is the ID current equals to zero, almost zero. So you can, like, it is like almost zero. So that will be the point of off, cutoff, or off point. Okay, so the Jfet has become an off or cutoff. Okay, so this is how the VGS controls ID is given. Okay, so the similar curve is given in the previous we have already seen. So this is the case where when VGS equals to 0 and VDS is greater than VP. Okay, so drain to source voltage we have applied greater than VP. At that time, the ID equals to IDSS. All these concepts we have already seen. Okay, just go through it. So ID equals to IDSS when VGS equals to 0. At that time, whatever the current will be, that will be IDSS. That will be a constant current. Okay. The next point is, when VGS is negative, we are going to reduce the VGS. Initially it is 0, now we are going to reduce it. Okay, so when VGS is negative, at that time ID decreases, the current will be decreasing and is constant above pinch off. So above pinch off, it will be constant, we have seen, and this pinch off will be less than VP. Okay, so this second pinch off is less than VP and the current has reduced. So initially it was IDSS, the current has reduced now. So it is less than IDSS. Okay. The next is, as VGS is made more negative, as we are increasing the VGS in negative direction, ID continues to decrease. So ID is going to reduce, but a constant above the pinch off. The similar characteristics will be there. Again, a pinch off will be there, and this pinch off will be lower than the VP also, and it will be beyond pinch off. The current will be constant. We have already seen. So the next is until, this is the cutoff case, until VGS is equals to minus VGS of. Okay, so when we are going to apply VGS, that is minus of VGS of, this VGS is a negative value, so it is written like it is of minus of VGS of, it is going to consider. At the time ID continues to decrease, when VGS is greater than minus VGS of, at that time the current ID is similar to 0. Okay, so up to VGS of, the current is further going to reduce up to here, but beyond this, beyond VGS of, the current is almost 0. ID is almost 0. Okay, so this is the point called cutoff point in case of Jfet. Okay, so this is the curves, all the characteristics. Another curve is called uh, transfer curve. We will just see also like what is the transfer curve, and this is the uh, figure showing the cutoff operation of Jfet. Here, this is the VGS we are applying, that is VGS of value. At that time, this is the case. Here, the depletion region has reached to touches each other, and there is no channel here. The channel width is 0, similar to the case where pinch off was taking place. So here also the channel width is reduced. At that time, the current will be flowing as 0 through the drain region. Okay, so this is the setup for cutoff operation of the Jfet. So one more point we will be saying is how the transfer curve is basically defined in case of Jfet. Okay, so transfer. So one, we have considered the drain characteristics. We have already seen this is the drain characteristics. So this is nothing but the drain characteristics. Okay, drain characteristics for different VGS value. So in the previous BJT case, we have seen the input characteristics and output characteristics. So output characteristics is nothing but the drain characteristics. But in case of FETs, we will not be plotting the input characteristics. Input characteristics is not defined for FETs. Can from here we can just write FET. Why? Because as we are going to reduce the gate to a source voltage, or gate source voltage is applied such that the gate to source region is reverse bias. So in that case, the IG, the gate to source or the gate current is always a 0. Okay, so in input characteristics we were plotting like the input curve, input current, okay, versus the input voltage. We were plotting this, but here in case of Jfet, the input current is always a 0. Okay, so there is no gate current is there, so that's why this input characteristics is not plotted in case of Jfet. So the another plot that is defined is called transfer characteristics. So we will be plotting the transfer characteristics. So transfer characteristics plot will be with respect to the ID. So ID will be the current, that is output current, that will be in milliampere, versus the input voltage. So input voltage, that is VGS. So we will be plotting the transfer characteristic that will be with respect to ID versus VGS. Okay. So the plot in the case of N channel of FET will be like this. So this is ID, that will be in milliamperes. Okay, with respect to that we will be plotting the VGS, and this VGS is in negative direction. Okay, so this is 0, this is negative side, so we will be plotting this. So here it will be like, as VGS is equals to 0, at that time the current that will be flowing is the maximum current. So that will be your maximum current, that is called IDSS. Okay, that will be the maximum. As we are going to increase the VGS in negative direction, the current is going to reduce. Okay, so the current will be reducing, and it will be reducing such that there will be a point when VGS off will be there, that current will be 0. So this is your curve. Okay, so this point at which the current is going to reduce to 0, this is called VGS off. So okay, so this is the region of operation that it is called saturation region. Saturation region, or we can call it like, here the current has become constant, and after that if we are going to reduce, or we are increasing the VGS, the uh, curve, that ID curve is going to reduce based on the decreasing or increasing the VGS in reverse case, or we are further decreasing. Initially it is 0, it is going to be in negative direction, so it is like it is decreasing further. Okay, so this is your transfer curve. So this transfer curve will be plotted for constant VDS. So it here the VDS is constant. So this will be the ID versus VGS for constant VDS. Okay, so here in Jfet the maximum drain current will be IDSS, and this IDSS is drain to source safe current. This is called IDSS, is called drain to source safe current. It is called IDSS, that is drain to source safe current. Safe current means this is the current that can pass safely through the Jfet. Okay, or it is also called drain to source saturation current. Drain to source safe current, or drain to source saturation current. Okay, and this will only be taking place when VGS is equals to 0. Okay, if in Jfet, if we are going to reverse bias the gate to source voltage, or gate to source voltage is going to reduce in negative direction, then we have already seen the depletion region will uh, further increase, and that will be reducing the channel width, so that will reduce further the current. Okay, so that current will be reducing because of the less number of charge carriers will be reaching to the drain side, that's why the current will be reduced. Okay, so this is the case. We will just see some more points. Okay, so here the minimum gate to source voltage that is required to cut off the channel, we know that is equals to the VGS off. Okay, so VGS off, or it is also called VGS cutoff, or it is called, sometimes it is called threshold voltage also. Okay, it is also called threshold voltage. So it is the voltage, it is the uh, minimum gate to source voltage required to cut off, it is the minimum gate to source voltage required to required to cut off the channel or to reduce the drain current to 0 is called the VGS of this. Okay, and also we know, as we are going to reduce the channel width. Okay, so the process by which we are going to reduce the channel width by varying gate to source voltage is called channel width modulation. So in case of BJT, we have seen base width modulation. Okay, so base width modulation or the early effect. So similar effect is also takes place in Jfet. So that is called channel length modulation. So that is called channel length modulation. So here the channel length modulation is uh, basically the process where channel width is altered or changed by applying or by varying gate to source voltage. So by varying the gate to source voltage, if we are going to change the channel width, that is called channel length modulation. Okay, it is similar to uh, a base width modulation, similar to base width modulation or early effect in BJTs. So this is all about your this drain and transfer curve of the Jfet. Okay, so similar analysis we can do for p-type p-channel Jfets also. Okay, so this is all about the operation of n-channel Jfet